So, kia koto, my name is Alice, and this project actually marks the completion of my master's degree in applied data science with the University of Canterbury, and this co-supervised by ESR and UC. So let's talk about this project. Groundwater is a valuable water resource for drinking water and irrigation, and this is especially true within the Canterbury region, where it has the largest amount of groundwater resources and also the highest use. The community water supply in Canterbury is from groundwater, and over 70% of irrigated land in New Zealand is in the Canterbury Plain, which also requires groundwater. So naturally, as the resident of Canterbury, we would like to know more about groundwater and how we can do to protect it. And land use is a known feature that has an impact on groundwater quality. It is also a feature that can be directly managed. So we would like to study its association with the groundwater quality. And before we answer that question, we first need to determine how do we measure the groundwater quality. And we use nitrogen concentration in groundwater as our quality indicator, because excessive nitrate can have negative impact on human health and the environment. So we seek to model its value. So to sum up our project objective, we will model the nitrogen concentration in groundwater within the Canterbury region and study its association with other features, including the land use. So let's first look at this illustration of the groundwater cycle. The recharge process starts from precipitation, and the rainfall first hits the land surface, and then it goes slowly through different layers of soil until it finally reaches the aquifer layer, where the groundwater gets stored. And this aquifer layer is a mixture of permeable materials that allows groundwater to flow slowly underneath the ground. So based on this illustration, we can have some ideas of what features we can include in our modeling. And here they are. We'll include precipitation and different types of land use and soil and hydrogeological system. We also include the seasons to account for the various patterns of the concentration under each season. And we also include some geographical features, including the ground elevation, the district of each well, and the distance from the well to the coast. And also include the depth of the screen. And the screen is the bottom part of a well that allows groundwater to come in. And we first need to detect whether land use is associated with different concentration. And these box plots are showing the nitrate distribution under each land use using the 4 versions of land use classification, and we can see that there are different patterns. And to test whether these differences are statistically significant, Kruskal-Wallis test and Dunn's test are used. These are essentially the t-test and ANOVA test, but they do not assume Gaussian distribution. So Kruskal-Wallis test produce small p-values for all the 4 years of land use. And Dunn's test were further used to detect the differences between each pair of land use. And the results are shown here. If there are stars, that means the differences are significant, and we can see that there are many of them. So these results tell us that the land use is associated with different nitrate concentration, and it is reasonable that we include this feature in our modeling. So here are some key considerations I did in the feature engineering stage. We first need to define the capture area, which means the area of land that's going to have an impact on the groundwater quality at the measured sites. I decided to draw 2-kilometer diameter circles to the northwest direction of each well. The reason is that the northwest direction is the general upper stream of the water flow in Canterbury. And at the distance of 2 kilometers, we can capture most of the nitrate from the land surface. And I then compute the composition ratio of different land use and the soil type within these circles to include as our features. And in this step, I had to address two issues. One is some circles are overlap with each other and some circles have some missing area as shown in this illustration. And the land use and soil type can have multiple levels of classification aggregation. And because we only have 359 sets in our dataset in the Canterbury region, I decided to use the highest level of classification and coalesce some levels to avoid overfitting. The precipitation data can be quite big. It is a daily estimate of rainfall that is done globally, so that requires some strategic processing to handle its sites. And I then calculate the mean rainfall 7 days, 30 days, 19 days prior to each measurement was taken to account for the time that it takes for the rainfall to reach to the measured point. And I decided to use the distance from the midpoint of the screen to the land surface as our well depth. And I also need to account for that some wells have multiple screens and some wells do not have the screen information, so that requires some sensible imputing. I only look at the lower side of the coast when I calculated the distance to the coast because of the nature of the geographical conditions, even though some wells are closer to the other side. And here are some key steps I did in the modeling part. In pre-processing, I used the mean coding to encode some categorical variables to numerical so that our numerical model can learn from them, except for some tree-based model that can handle categorical variable directly. And I did cyclical encoding for the seasons to account for the circular nature of the seasons. I standardized my feature to make sure that they have unified mean and variance. And resampling is required in training models, and this involves the initial training test split and also the training validation test set split during the cross-validation. And two methods were used. One is group-based resampling and one is without group-based resampling, so which is the conventional random sampling. Because we have repeated measurements from the same sites, and group-based resampling ensures that the measurements from the same site only appear in either training set or the test set. So when we evaluate the model's performance, we would get an indication of how well the model can generalize to future unseen sites. Whereas if only the random sampling is used, we can still predict future nitrate values, but it will be more suitable to use it only on the existing site. I use tenfold cross-validation and make sure that the folds are consistent across different model tried for fair evaluation. And I did manual feature selection as well as using the model that can do feature selection directly. And here are the results of some of the models I tried. The box plots are showing the RMSE distribution across the cross-validation folds. And the lower the RMSE is, the better the model is. So the best model is highlighted there. It is a random forest model from the Ranger package. I do note that these models are tried, all used group-based resampling. So the best model's performance are recorded in this small table to the left. The training R-squared is 0.32, which means 30% of the variation in the response variable can be explained by the model. And the test RMSE, which is the best model performance indicator, is 3.21. And to help us better understand what this number means, here's a bit of context. The measured nitrate is between 0 to 28, and the majority of them are under 10. On the other hand, the models without the group-based resampling are much more superior. As you can see, here is the performance of another model, another random forest model. and the training R-squared is 0.86. That means over 80% of the variability can be explained. And the test RMSE is 1.71, which is a lot better than the previous model. And here are some videos showing more details of the model's performance. The model with group-based resampling are shown on the top two plots, and the bottom two are without. And the training performance are on the left, and the test performance are on the right. And these are predictions versus actuals plot. That means if a model performs well, the data points would be more aligned to the diagonal line. And you can also see some orange data points moving around. Those are the data points within the same sites. So we can also see the within site performance. So in general, the training performance will be better than test performance, which is also the case here. But we can see that the model without group-based resampling is performing better than the top two ones. And if we look more closely, we can also see this horizontal spread, which is more prominent in the top right plot. So this means the model tends to predict constant values for this set when the actual values can vary. And this is because there's some features do not have that much variation, hence the leverage to explain the variation in the response variable, and additional features might be required to improve the model's performance. And here are the plots of the variable importance. And these are from the two models that were shown. And it's a bit hard to read what each variable means, so I got together these two small tables. They're showing the top 5 most important variables. When group-based resampling is used, land use is the most important variable, and specifically low-producing grassland is associated with lower nitrate concentration, and annual cropland is associated with higher concentration. So this means farming activity does have a positive association with the nitrate. And when group-based resampling is not used, the district becomes the most important variable. That means the model is relying a lot on the locations of the well to make predictions, which contributes to the improved performance. So in general, our methods is effective in learning about the existing sites and make predictions for the existing sites. But it can be challenging for the model to generalize to future unseen sites. And I face some challenges in this project. For example, we have a mixture of well depths, so which means is challenging to accurately define a capture area for all the wells. And additional features that can have an influence on groundwater, but not included, such as irrigation. Irrigation activities has a huge impact on the nitrate concentration in groundwater, but that data can be very hard to acquire. And we also haven't accounted for the complex hydrogeological dynamics for the groundwater and the actual human activities that's happening on the land surface. So in the future, if we want to improve the model's performance, we would try to include the mentioned features and also focus on a selection of wells that have known similar conditions. That's all. Thank you.